So I'll start today talking a little bit about sea surface temperatures and why we want to use them in ice-ocean interactions and understanding them in Antarctica. I'll talk about the Landsat single channel algorithm and then some of the new techniques that we're applying to use them. So I want to first recognize a lot of the collaborators that I have in this work that I'll show you today from across the globe and the US. So starting out, just a little bit of background on Antarctica. So this is Antarctica, obviously important for climate change. Around Antarctica, we really worry about sea level rise, especially coming from West Antarctica, but this is kind of a wild card in terms of how much melt it will produce and contribute to sea level. So we really need to understand West Antarctica over here, especially for over the next coming decades. In Antarctica, all of the melt from around the continent occurs at the glaciers and ice shelves that are shown here in the blues and purples by the relatively fast-moving ice that comprises them. And of this melt, 50% of it occurs as basal melt coming from the ocean. So ocean heat transport is really important for Antarctica. Around Antarctica, the ocean circulation or the ocean water masses that are here are winter water at the surface, which is cold and fresh. And then circumpolar deep water usually resides below 300 meters and it's salty and warm. And the circumpolar deep water is what you usually worry about bringing heat towards a lot of these glaciers in West Antarctica. In Greenland, there's an analog to these, which is polar water at the surface and Atlantic water at depth. The way that this heat is transported towards the glaciers, it comes in at depth, it melts at the grounding line, the last place where the ice meets the ground before it begins to float as an ice shelf. That melt is fresh and buoyant, so it rises towards the surface as a plume, and then it exits away from the ice shelf, either away from straight out or parallel to it, depending on where you are. But this circulation process draws in more warm water and creates more melt. Around Antarctica, there's been a recent increase in the amount of data that we've collected. So International Thwaites Glacier Collaboration is one instance of this, where a lot of people are taking measurements of the atmosphere, ice, and ocean to better understand these processes. There's a ton of data coming out of this, but when we think about studies around Antarctica in general, the data is very sparse. So there's a lot of red on this. The red is showing where we have measurements around Antarctica. But what you'll notice is that in the light blue areas around the continental shelf, we have very few measurements of what's going on in the ocean around Antarctica. And to fill that gap, we can potentially use remote sensing. So this is NASA's satellite constellation. There's other space agencies we can use remote sensing from, and these can potentially provide or fill in the gaps that we have in the field observations, because all of the big data that we have is really from the last decade. And there's very little before that. So a lot of the work that I'm doing is trying to understand ocean heat transport towards the ice using remote sensing. And one of the pieces of work that I've already done is in Greenland, showing that we can use sea surface temperatures around the continent in some locations where the oceanography is correct, as a proxy for surface and subsurface water temperature. So we've specifically looked in southeastern Greenland, especially when it's wintertime, the sea surface temperatures can tell us about the water column down deep because the surface water column is homogeneous and there isn't solar radiation creating a thermocline at the surface. So in places where we have warm water at the surface, and then it circulates down deep, down to 300 meters towards the coastline. In those places, we can actually use sea surface temperatures as a proxy for understanding the water temperature variability. And then on top of that, we can also use it to track circulation because of the temperature differences in the polar water. This is Greenland again, and Atlantic water. So here in this study that we've done, we can use the rich data set that sea surface temperatures provide to see circulation events that are huge. This crosses the entire continental shelf, goes 40 kilometers. Is an intrusion of Atlantic water that covers 40 kilometers over the course of a few hours. And because we have this high resolution temporal capture from MODIS, we can see this in southeastern Greenland. And this is something that you would never be able to capture with field observations unless you had a huge array of data. So this intrusion is coming up a trough, a bathymetric trough. It's stimulated by that trough. It transports Atlantic water towards the coastline very rapidly and warms the water down deep that is heading towards a glacier, a big glacier in Greenland called Helheim Glacier. And so we get to see a much better spatial and temporal, or we get a much better spatial and temporal capture of the surface, at least using sea surface temperatures. And it allows us to see the entire coastline as well. So here we're seeing some of these intrusions occur simultaneously along the southeastern portion of Greenland, along multiple different troughs. And we can show that now that this sort of phenomena is really important for transporting heat in this area. And so not only can we use it to kind of improve or fill in the gaps in the ocean field observations that we have, but it also, thermal actually provides us new opportunities for studying Antarctica in wintertime. So this is what Antarctica looks like in wintertime. There's no solar radiation. So this is what it looks like in visible imagery. But in thermal, we can start to see the surface really well because no solar radiation means that the surface temperatures can be captured much more easily. And so this is a 68 iceberg that's being calved off of Antarctica at the Larsen Sea ice shelf. You can see some of the surface topography in this imagery, some of the suture zones in the ice. These are pretty fine details for the ice shelf. And you can see leads and things in the sea ice. So you can start to study these things in wintertime. However, MODIS was capturing, or does kind of capture, a lot of this information in Antarctica, but for the most part, thermal is not captured in Antarctica in wintertime because nobody really thought that it was important. So until we started turning it on to look at iceberg calving events in Antarctica, there was no imagery from wintertime, only summertime. And now the wintertime imagery is only just starting to be captured literally this year. So there's maybe one summer that, or one winter that was a special acquisition a couple years ago in 2019, and then this data. So we've missed a lot of the rich information we can gather, at least using Landsat. So it's been really nice, at least, that sea surface temperatures have been captured around Antarctica and processed year round. So we do have that record, which is really cool from MODIS. So I'm really interested in studying these kinds of features, ice ocean features. So I need to use Landsat in a lot of these situations because some of these features are very fine scale. However, Landsat doesn't produce, the Landsat science team does not produce a single channel algorithm at the moment for sea surface temperatures. And so out of necessity, I had to start developing my own. And recently I've been working with Andy Harris and Chris Merchant on this work to develop a useful Landsat sea surface temperature algorithm that's single channel for Landsat 7 and Landsat 8, which has covered since just about 2000 is when we started really capturing a lot of that data. So in this work that I've done, I've worked with them to really build a robust atmospheric correction, and this is still underway, but I've done all of this work in an open cloud workflow to make it faster and to make it more accessible and transparent to the scientific community at large. And so I'm going to walk you through this algorithm really quickly and talk about how we're doing this in the cloud to streamline this and not, hopefully soon, not need to download anything, but all of this is automated. So in this, we can, in this algorithm, I use Python. We can search the Landsat catalog, lazy load all of the Landsat bands. So that's the code that you see here on the right. We use DASC and XArray to do this. And what lazy load means is that we can open the data set using the metadata only. And that once that metadata is loaded, DASC will do a lot of, or layer all of the computations without actually conducting them. So until you need the outputs and values themselves, all of the computation is being done using the metadata. And so you don't have to do, you can subset and things like that and only capture portions of the data using this lazy load because it is in a cloud optimized format. From there, I create an initial cloud mask using the QA band from Landsat that's built using the CF mask algorithm. But then I do an additional classification for cloud, ice, ocean, and land because the CF mask is pretty crappy in Antarctica. And I have to build a separate classification algorithm to pick out these features. So we've done that using PyTorch. I'll talk a little bit more about that in a moment, but that's using a neural net. From there, we do an atmospheric correction. And we use this equation here. We're simulating the coefficients using ERA5 atmospheric profiles and sea surface temperatures to simulate that and get at those coefficients. And we will eventually account for water vapor, view angle, surface emissivity, and month of the year in that. And then from there, we generate the sea surface temperatures, we mask them, then we acquire water vapor from the closest MODIS scan to Landsat because Landsat doesn't have the bands on board to make that correction. And from there, we search, download, and read in the Modo 9 atmospheric data. And as I mentioned before, we're working really hard to automate and prevent from needing to download anything. But there's problems in our data right now because the data formats that are provided and served in the cloud are not possible to open in the contemporary Python packages that we have to be able to open them directly from URL. So even though we're streaming this data in the cloud, because these are in legacy data formats, this is in an HDF EOS file format, we still have to download and convert the data. There is code to convert the data format, but we still have to download the data. So that's being done all in line and automatically, but this is a problem. If you take anything else from this talk, please, please, please put all of your data products in, if nothing else, NetCDF, but ideally cloud optimized data from here on out, because we can't open the legacy data formats anymore with in contemporary software packages. From that, we align the Landsat and then we apply the atmospheric correction. That whole process takes about 75 seconds. From there, we calibrate using MODIS sea surface temperatures. So I'm using MODIS as a calibration data set because there is very little calibration and validation data in Antarctica. We're hoping to improve that in the future. MODIS is not great for the same reason, but it's the best thing that we have. The data that I'm showing here was kind of done very quickly at the end of my PhD. And so this will just be improved as we move forward, but we find nice alignment with Landsat and MODIS to use MODIS as a calibration and using a Landsat regression. So we'll just be working to improve that. This is just an initial run at this. From there, I created a time series at Pine Island Glacier in Apollonia here that's about 5 kilometers across and has a plume that rises there that is relatively warm in comparison to the area around it. So this area is open water year round, and it's really important to be able to track that plume. So we use sea surface temperatures there, and this is the record that we kind of get from Landsat from that. So that's kind of the algorithm that I'm working with, and I'll just talk briefly about a few applications that we have for using thermal and sea surface temperatures around Antarctica right now. One application that we're using it for is to detect Antarctic coastal current by integrating thermal remote sensing and field observations. We're also using it to detect warm plumes with the aid of machine learning. And then from there, we're going to, I'll talk about some of where we're going next, which is taking this big data and doing some ice ocean analyses with it in the cloud using open science principles. So some of the work that we're doing is on the Antarctic coastal current. It's because the currents around Antarctica are almost completely unknown. You'll see this map here down at the bottom showing the Antarctic coastal current path around Antarctica. There's been work in the Antarctic Peninsula to show that it exists along the coastline. It flows to the fast and towards the west, and it carries a lot of meltwater in it as it passes by the ice shelves. And that meltwater can impact deep water formation as that current runs towards this area in Antarctica where deep water is created for the entire globe. So it can impact global circulation. And it also can impact the amount of heat that's transported towards glaciers. So it's pretty important. And as you can see, there's very little of it that we understand around Antarctica. So I want to use sea surface temperatures to help understand the spatial and temporal variability in that, because this current is at the surface. And we can do that in some locations because the coastal current is warm or is cold at the surface in summertime because meltwater is within it, and meltwater is relatively cool compared to the ambient water temperatures. So here, this is an image, a sea surface temperature image from Antarctica from the Amundsen Sea in summertime. And the blue here is relatively cool, where we expect from modeling outputs to see the sea surface or the Antarctic coastal current at the surface. And so we can see cool water temperatures here and here. These are locations that are directly downstream of ice shelves. So we expect that we have this meltwater as a tracer there. There's other locations that we can't do that. And that's because we don't have that source directly upstream. So in some of these locations, we can expect to be able to use thermal and sea surface temperatures. And these are examples of the sea surface temperature record that we have there. So this is looking down on Thwaites Glacier, which is all ice here in the southern portion of the Amundsen Sea. This is obviously the ocean and sea surface temperatures. These are icebergs and clouds that have been massed out. And this is where the Antarctic coastal current is. It's being highlighted because we have outflow from Thwaites Glacier of melt. And this is it over from December 2016 to January 2017. So this is a record that we would never be able to capture with field observations, because the ship wouldn't be there and it wouldn't be sitting there for that long. So we can start to do basic things like measure the width of the coastal current using thermal infrared and sea surface temperatures. And this is just the initial record that we got from 2016 to 2018. This is the coastal current width using Landsat. And this is the month of the year from December to January. So you can see multiple different years and what they look like seasonally. And what you'll notice is that they kind of center around 15 kilometers width. And this is similar to the width of the coastal current we would expect based on the basin configurations in the area. But you'll see some variability across that, which may be related to changes in meltwater, diversion of the coastal current away from this area, and potentially widening and narrowing of this coastal current during storms. And there's also potentially errors in the method. If the tracer isn't working the way that we expect it to because of changes in meltwater, then we may see some variability in that. But overall, we're seeing some really interesting seasonal and interannual variability that we can capture from thermal that we wouldn't otherwise. Another feature that we can study are polynyas, persistent polynyas around Antarctica. So these are open water areas that are opened up by that warm water that rises towards the surface as it melts the base of the ice. So what's really cool is we can see these from remote sensing. They carry a heat signature, and so we can study them using remote sensing. So we want to investigate how these vary through time and how that relates to the mechanisms that may drive them, and how we can better understand what's happening beneath the ice shelf using these. And so this is kind of a zoom in of that. So these are what the persistent polynyas look like. They occur at the end of these channels that I won't get into, but these are carved by the plumes as they rise. So these are persistent features that occur over multiple years. And we're automating the detection of these using a cloud-based workflow and machine learning. And we're using Landsat, MODIS, and Sentinel data, so it's being fused to get at basically an outline of these persistent polynyas. And we're using information such as the fact that it occurs at the end of these channels and at the front of the ice shelf to be able to improve detection. And using that deep learning method, we can create a time series like this, looking at how that polynya varies just in size. And we'll be using thermal infrared to study how the temperatures change through time in comparison to the ambient ocean temperature. So we can start to get at these small features. This feature is 1 kilometer across. We can study these around all of Antarctica because there's something like at least 30 of these around Antarctica in places where a lot of melting is occurring. And we can do it in an automated way. So this is what big data is allowing us to do, is to look at these small features, every single image that we have over multiple decades. And the way that we really harness the power of being able to do this and automate it is using the cloud. And so someone you may recognize, Shel Gentiman, is now a program officer at NASA in charge of the Transform to Open Science program. And she has really pushed the idea that cloud computing is a way that we really push ourselves into a new space to answer new different kinds of questions and to advance science and inclusivity simultaneously. And so some of the tweets that she's shown have shown that we can use cloud computing to democratize science, that no matter where you are in the world, no matter what kind of computer you have, if you have a little bit of internet access, you can be able to do the sorts of processing on sea surface temperatures or any other science data set that you like. And so the cloud kind of works as this place where data can sit in the internet, because that's what the cloud is. Data sits there instead of having to download these huge data sets. You can stream it automatically. You put the important software tools that you have in that internet cloud space. You design them specifically for the work that you're doing. It's all done right in that one space, and it happens more quickly because it is all in one place, and it doesn't need to move around the internet or across your internet connection to be able to do that. And the data read-ins are 2 orders of magnitude faster than they would be on your own local computer. And so we're able to do things like use big data, integrate disparate data sources, have participation of diverse communities, and ultimately connect with society and impact critical decision-making on timescales we've never been able to do before. So much more rapidly. And so one of the things that I've done in my work most recently is to create a cloud computing platform to be able to do that for cryosphere communities. This includes some work on ice-ocean interactions, but also a lot of the rest of the cryosphere community. And we've done that with the ISAT-2 science team. So ISAT-2 is a satellite that captures surface elevation of the planet. And the science team for that meets once a year or twice a year. And I was a part of that science team meeting last year in May, where they expressed a lot of concerns about the cloud being expensive and having non-intuitive structure, pricing structures and infrastructure and that sort of thing. And myself and Joanna Milstein, who's a graduate student from MIT, who are sitting in on this conversation, thought that we could do better. We've had experiences that are much better in the cloud, and so we decided to design a cloud computing platform with bumpers. So it's a simple and cost-effective managed cloud environment for training new users and transitioning to cloud workflows. And it'll allow us to do processing pipelines like sea surface temperatures much more rapidly, and allow people to learn how to do this transition in a much more controlled and thoughtful way, so we don't have people spending a ton of money trying to create this cloud infrastructure from scratch. And so we're working with the Interactive International Computing Collaboration to do that. And they have a lot of cloud expertise to streamline this process and make it easier for our scientists to process data and democratize science. So they can build these algorithms like y'all do with sea surface temperatures. So we built this cloud computing platform that will be persistent for at least 3 years. We provide small instances for all of our users and the option to use larger servers if you bring your own AWS credits. We're developing new tools that will be added to the Jupyter infrastructure and ecosystem. And then we're helping to I2C to scale with community surveys, feedback, and guidance. And if you want to check it out, it's here at cryoonthecloud.com. We have our Jupyter book there, which has a lot of the material for being able to access data sets, all of the up-to-date things. The processing pipeline that I just showed you from earlier for Landsat, some of those tools have literally started working and coming online within the last couple of weeks. And a lot of our tutorials have already captured that. So if you're working in the cloud, you can have the up-to-date tutorials on that. And then our hub, our Jupyter hub is there as well. You can check out our GitHub with all of our code. We have a Slack channel, community office hours, and we're bringing in related cryosphere communities to be able to share in the ideation and construction of infrastructure that allows us to interact with all the disparate data sources, bring people in. If you're working in HPC, how do we interact with an HPC from the cloud and bring that data in and out easily? Those sorts of questions we're kind of working on to speed up this sort of data processing that we do. And so what we end up doing is we bring a lot of different kinds of users into CryoCloud. We have all of our data sets that we can access. The tutorials I have show that the tutorial is on the left here that brings together ISAT-2 data, MODIS data, and Landsat data into one place. And the developers for the software packages that access those are also in those same locations. So IcePix is ISAT-2 centric. Earth Access is for NASA, accessing data from NASA. Earth Access is the one that is recently come online and been streamlined in the last few weeks. And so the developers are in the same kinds of environments in this cloud environment that all of the users are. And what that means is that we can accelerate feedback and collaboration, because as something gets developed, our users can instantly start using it. When they have issues, they can report that back immediately. And because they're working in the same environment, we can really start to respond and fix a lot of the bugs that we have in these tools to do the cloud computing that we need in a more streamlined process. And what that ends up creating is open science as a process, not as a product. So really changing the climate and community structures so that we can collaborate and communicate much more easily within our research areas. So cloud computing is kind of the future. I know it's the sea surface temperature products. A lot of them are in the cloud right now. And I have a lot of code for accessing this if you want to test it out. The parts of science that are really time consuming can be getting your environment and getting the data for data access, or the code for data access put together. And those things are already provided or built by myself and some other people. So if anyone wants any of those, you can definitely reach out. So that was just kind of a whirlwind of what we do with sea surface temperatures and why I'm working on Landsat sea surface temperatures specifically. So I'm going to end there and let everyone ask questions if you like. These are my funding sources. So yeah, thank you very much, and reach out